Hello everyone, thank you for coming for today's talk. Today we will be discussing explainable artificial intelligence techniques and how they can be used as a conventional data analysis tool. So first let me introduce myself. I'm Maria Sahakyan. I'm a postdoctoral associate at New York University, Abu Dhabi in the Department of Computational Social Science, and I'm here because I really love to share my knowledge about explainable AI. So machine learning, before going to explainable AI, first let's talk about machine learning a little because we are connected. So machine learning techniques is gaining attention, especially recent decades. The attention to machine learning simulated a wide variety of models which designed to make decisions in different domains across academia and in industry. So machine learning is very involved in our lives. It's even more involved than we can ever imagine. It starts from basic movie or song recommendation on one hand, moving to criminal justice and electronic health record management on the other hand. And the recent implementation of machine learning and artificial intelligence was the self-driving cars. Given the criticality of domains that with machine learning and artificial intelligence techniques are implemented and used, it is very important to have highly accurate models because one simple misclassification might affect someone's life. Moving through the idea of machine learning is it takes historical data, learns in the training stage, and then predicts on the testing stage based on the data that it learned from. Let's say we have a simple example to demonstrate. Let's say we need to decide here, not we, but the machine learning model needs to decide here, is it a husky or a wolf? So in this one, it of course predicted correctly, but in the next example, we got a misclassification. And it can be especially dangerous if someone wants to adopt a husky. Anyway, so what was the cause for misclassification in this case? It was the snow, because in the historical data, a lot of wolf pictures had snow in the background, and machine learning models got confused in this situation. But we don't really know about the reasons behind each misclassification because the highly sophisticated models used and the users don't really understand how the model came to certain decision. How can we deal with misclassification? There are two solutions basically. First, we can use the simpler models, which are logistic regression, linear regression, or decision trees, or we can continue using the highly sophisticated model coupled with explainable artificial intelligence, about which we will talk a lot during today's presentation. So what's the problem with the first solution that I mentioned, which was using the simpler models? It is because when we are looking with a graph of accuracy and explainability, we can see that these simpler models are on the part of the graph that explainability is high, but usually accuracy is not that high. So there is always a trade-off between accuracy and explainability, and the higher we go to higher accurate models, the less explainable they are becoming. To explain, to highlight the importance of explainability, I will just bring a simple example. Let's imagine we have applicants who applied for the loan, and the analyst who gathered the data, he is feeding this data to machine learning model, and the model basically is making an automated decision who would get the loan and who would not. Based on this model's decision, let's say someone who was rejected in the loan, he's confused why he was rejected in a loan because he has really good salary and good credit history, and then he comes to this analyst to know the reasons. The analyst doesn't know because the decision was automated using a highly sophisticated model. Now let's imagine the same situation, but after using this machine learning model, analyst also uses explainable AI, and after using explainable AI, he can zoom in on each applicant and see which features affected the decision of the model. Let's say the first one had master's degree, had annual salary which was quite high, and because of this zooming in, he will have answers for every applicant who wants to know the answers why he was rejected or why he was given the loan. So basically, we can imagine explainable AI techniques are kind of local feature importances for each of the applicants who wants in terms of the features. Moving forward, I want to show how attention has increased towards explainable artificial intelligence in recent decade. Let's have a look at some statistics. So what I did a basic search in Google Books Ngram, which also a search in Web of Science and Google Trends. From all of these graphs, we can see that attention towards explainable AI started increasing starting from 2015. Moreover, the papers that are talking and mentioning explainable AI techniques, they are getting published in really good journals and getting high citations, like around 4,000 to 8,000 in just 4 years. So having this increasing attention towards explainable AI, the research question was, is there a way to utilize these explainable AI techniques and use them as a generic data analysis tool, and how can we benefit from this? So before going and exploring explainable AI techniques and understanding how can we use them, let's first understand what are the usual data analysis tools that are used in the literature nowadays. And we can see that the trend that has development, a parallel trend with development of data analysis is regression analysis, which is very widely used across every discipline of science, starting from medicine, going to economics. These are the papers, number of papers in a number of journals that use regression analysis in their, so we can see it's quite popular. Having explained importance of regression analysis and also seeing the attention to explainable AI, we can go finally to the focus of today's talk. So regression analysis gives us a global view to the features, to the data. And on the other hand, we have explainable AI that we just discussed, that it is giving a zoomed-in view to each of the instances. So now the question is how to obtain a zoomed-in view having the instant view, how to obtain a global view having the instant view, which is we can use coupled regression analysis together with explainable artificial intelligence. Now I will explain how we would do that, but first let me quickly go through which kind of explainable artificial techniques there are in the literature, so we understand which part of this graph we focus and which kind of explainable artificial intelligence techniques we will be using for our analysis. So let's say we have data in the black box model. Black box model, we don't know how made the decision, and we have the outcome. There are three types of explainable AI techniques, which are model explanation, model inspection, and outcome explanation. So model explanation techniques, they are giving explanation to the logistics of the models, how the weights are distributed, how the models are working internals, and also it is usually working this way. Let's say we have a neural network, it is a very complicated model, and after that we are using a simpler model, for example a simpler decision tree, to track how that neural network on each state made the decision. So basically a simpler model is replicating a more complicated model, and these kind of techniques are model explanation techniques. Model explanation techniques are usually used to give visual or textual explanations to the users throughout training the model. And it is like, for example, sensitivity analysis and some visualizations that can help the user to understand each stage of the models, how something changed or what happened to the model. And the outcome explanation techniques are the techniques that are not explaining the model internals, how the model worked, but only explaining the decisions of the models and how what is behind of each decision for the model. For example, let's say someone was rejected in the loan, like for that person, each feature, how contributed for him to be rejected or how contributed for him to be, like it's local feature importances as we already mentioned. So having this said, our focus is on the upper right part of these models, which is outcome explanation techniques. The reason that the focus is on this part is because the outcome explanation techniques are giving us the coefficients the same size as the data that we feed to the model, and we can use these coefficients to have more sophisticated view to this data set. And among these outcome explanation techniques, I have chosen SHAP, which stands for sharply additive explanations. I will explain it in details in a bit. And it is a most recent explainable AI techniques, and it's cited around 8,000 times, which is quite a lot. Anyway, to explain SHAP and to explain how we can use it in our regression analysis, I have to explain first Shapley values, which is from a cooperative game theory. Let's imagine we have players and we are playing a game. So these players, it is very important to understand how much each player contributes to the game. First, if we have 3 players, we need to consider all their possible joining orders, like which one joined when and how much contributed to the game. If we have, in this case, the value of the coalition is fixed. Let's say red player joins first, and if red player joins first, we can see that from the first picture that if red joins first, she brings only 10 to the game. We know also that the coalition value is fixed. For example, if red and blue they are playing together, their value should be 50. It means if the blue player is joining the second, not first, he needs to add as much value to the game to reach 50, which is 40. But in case the blue player was first and blue player brings always 30 to the game and the red player joins second, this time she needs to add as much to get 50, because their coalition value is always 50, which means she needs to bring 20 to the game, and so on. So if we have 3 players playing this game, we have 6 joining orders. And then to calculate the Shapley value, which is the marginal contribution of each player, we need to see from each joining order how much this player added to the game and divide it to the number of joining orders. So calculating Shapley value, it sounds like easy in example with 3 players, but it is usually computationally very expensive, because when we add one more player, the number of coalitions is increasing exponentially. So Shapley values usually cannot be calculated for bigger number of players. However, we can estimate it, which does SHAP, which builds the explainable AI technique, which builds on Shapley values. So what SHAP does, let's imagine we have a data set, and instead of players, we have features. So each feature is a player, and each feature adds some value to the coalition of features. So the value of the coalition, which is, let's say, red and blue, is 50 in this case. In that case, the value of the coalition is the quality of outcome of that instance. So what SHAP does, it takes all the features and takes all the possible coalitions of the data features and then samples from these features each time. And then on this sample, it runs local models, let's say regression on feature samples, and then samples again with other features from this same feature set, and then sees if this feature was in this sample on the first sample and was not on the second sample, how much was the difference of the quality of the outcome, and how much that feature could add to if that feature joins to this order. That's how SHAP estimates the coefficients of each feature, the importance of each feature on instance level. So having explained the Shapley value, now I can talk finally what output SHAP gives and how can we use it. So let's say we have n times m matrix with 4 features, which is our data set that we want to get explanations for, and then we train a machine learning model on this data set, and let's imagine this time it's a binary classification, and we have minuses and pluses as an outcome. So SHAP takes as an input the data set and the trained model, and it makes the same, its output is the same size matrix as the input data, and but it ranges from -1 to 1. -1 being like a negative effect of the feature to the decision of the model, and 1 being the most positive effect of the feature on the decision of the model. For example, if someone was rejected, again in the loan, -1 salary, it means salary really negatively affected if we have coefficients for salary -1. So the pipeline of using explainable AI as a conventional data analysis tool is as follows. Let's say we have a training data, and then we do, of course, we get the training data, and the real life data is always very messy. So we need to do data cleaning, feature engineering, and feature selection. And then we need, this part is very important, we need to address the imbalance and missing data issues, because although some machine learning models can take missing data as an input, for example, like GBM, but SHAP doesn't take missing data as an input. So we cannot feed any data with missing values to SHAP. After this training the model and cleaning the data set, we feed the clean data set and the trained model to a SHAP algorithm, and it generates the coefficients matrix the same size as the matrix we feed it. But so the suggestion here is that we cluster this generated new matrix of SHAP coefficients, and instead of running our regression analysis on the first having the big picture on the initial data set, we run regression analysis also on these clusters based on SHAP values. And running regression analysis on these clusters based on SHAP values, it gives us a very interesting point of view on a data set, which I will show you in a bit, because I have done some experiments. So for those who doesn't know who is clustering, what is clustering? It is just grouping similar, let's say we have a data set and we need to group similar data points together so that the data points in the same cluster are more similar to each other than the data points in the other cluster. So the most basic clustering technique is k-means clustering. So in this pipeline with here we were suggesting clustering. The user can use any type of clustering, although the k-means is very easy and fast to use. And let's say we have this outcome matrix of SHAP coefficients, and then we use k-means clustering plus Kalinski-Harabas index. So Kalinski-Harabas index, it is basically an index which is calculating, which is helping us to understand how many clusters do we need. For example, with k-means clustering, if you want to run k-means clustering, you need to specify how many clusters do you want, and how do we find this optimal number of clusters? It is, we do the clustering and we use Kalinski-Harabas index on them, which calculates the index between cluster, which is an index calculating between cluster dispersion and inter-cluster dispersion. And that's how, if we have a higher Kalinski-Harabas index for, let's say, 4 clusters, it means we need 4 clusters on SHAP coefficients. Anyway, so here I will bring the example with, on a real data that I trained these models and got SHAP coefficients to show how this regression, clustering and regression works. So in this example, it was it was a credit default data set. So we needed to predict if some applicants, they can pay the loan or they will default. So when we do this regression analysis, in this case, because it was binary outcome, we did a logistic regression. We can see this is the odds ratio of the features, and we can see that the most important feature is credit to annuity ratio. Of course, if you're applying for the loan, then it comes the down payment rate. It is also one of the important features, and mean of external sources, which is the external money from external sources that the applicants get. So it's all about money, as we can see from this importance to the loan payment and amount of annuity and income to credit percent. Anyway, so all the important features that we can see from logistic regression are all about the income of the person and how can the person cover the credit. But then we move to the SHAP clusters analysis. The way that it was suggested to use k-means clustering and then do the regression analysis on these clusters, or we can do centroid analysis, doesn't matter, both gives really interesting results. And we can see that we got 4 clusters when we did this k-means clustering, and it's important to mention that on this big data set that was, we were predicting a credit default, the default probability was 0.4, so 40% default probability. So based on these sharp coefficients, the clustering was done. We can see that it clustered the people on who has higher default probability in the first cluster, and the people who have low default probability in the last cluster. And what is very interesting for me in this case, we can see that the most important features in the first cluster that people will get a higher probability of default was, of course, credit to annuity ratio, credit to goods ratio, which is like what goods people applied for the loan to get goods. But also it was interesting that email that they provided, or their email or no, they provided their work phone or no, it was also very important features in this case. So in this type of clustering, when you do this type of clustering and you do the analysis on these features of local levels, because these features, coefficients that SHAP gives us, they are local feature importances, we can see some features that are important for some people which are not important for some other people. And if we use a regression analysis on normal data, we would never pay attention to if person provided email or didn't provide email. But in this case, for this group of people, it is an important feature. So this technique helps to shed light on the data set and look at it in different perspectives to highlight features that we would miss for sure if we use the normal data analysis techniques. Anyway, so when this clustering was done, of course, so someone might ask question, let's say you didn't do the clustering based on SHAP coefficients, but you did the clustering based on the data, and why wouldn't clustering based on the data wouldn't be as good as clustering based on SHAP coefficients? That's why I did also clustering based on the data to show that it's not as good as clustering based on SHAP coefficients in this case. And so in this figure, we can see that we can see that we selected the most important features based on the initial logistic regression analysis, which was credit to annuity ratio, credit amount, and current debt on credit bureau. That like if we need to know how much debt in total the person has. So these 4 features, we wanted to show the distribution in the data, in the clusters based on data, and in the clusters based on SHAP. And we can see that clusters based on data, we are just replicating the data distribution of these features itself. But clusters based on SHAP, these features are distributed really differently. And in first cluster and last cluster, we can see that the features are high and low, and the default probabilities are 0.71 and 0.11, although in the clustering based on data only, the default probability was around 0.4, which is the default probability in the whole data set. So it means this clustering didn't give us basically much information. Also, when we did this clustering based on SHAP, based on data, and we did the logistic regression on the whole data set, we wanted also to show the performance of these logistic regressions on each of these SHAP clusters and each of the data clusters. So we can see that, for example, when we did logistic regression in the whole data set, our R-squared was 0.18. So R-squared is the goodness of fit, how features are explaining the outcome variable. So if it's 0.18, it's not quite well explained. It means the features are not very well explaining the outcome variable. But when the clustering was done based on SHAP and the regression was run on each of these clusters, we can see that the average R-square increased from 0.18 to 0.36, which quite a good increase. So this was calculated, the logistic regression was done on each of the clusters, and then the weighted R squared was calculated based on cluster size and taking the R squared of each cluster. And and we can see that R squared increased, and also the accuracy also increased. It increased from 0.84 to 0.87 in case of sharp clusters. So basically that's it. But I wanted to know how much time we have, so I could demonstrate if I could demonstrate something else. Okay. Actually, you can ask. I wanted to say you can ask your questions, but I want to demonstrate how easy it is to use sharp in 1 second. Okay. So I wanted to demonstrate on this example how easy it is to use sharp in Python, because the people who are using the usual data analysis techniques and regression, they would say, why would I go to this much hassle and train a model and then use sharp, and who knows how difficult it is to use it, etc. So I wanted to show that it is very easy to use and generate the coefficients. Here I used the Titanic dataset. It's a well-known machine learning dataset, a small one, because I just wanted to demonstrate how it works. And then we have here the target name, which is did the person survive or didn't survive, and we have some features like what sex the person had, age, what kind of ticket the person take, and etc. Is the person alone or family, and what was the reasons that people survived or didn't survive. Anyway, so this is Jupyter. This is a Jupyter notebook. Google. It works in Google Colab. This is based on Python 3, so it's basically online Python. I'm usually using it for my work, but it gives only 12 hours to work on. Anyway, so this is Python-based environment, and I will show how it will be implemented. So these are the features of the dataset that I explained. Now how sharp works, we just need to pip install it before we move forward. It's a very easy and fast installation. Anyway, here I imported some libraries that I will be using during this analysis. Then, okay, so this is the data loadings. I did some feature engineering, for example, fill the missing data, and so I distributed age so that we will have age code, like from which age range is the person. Anyway, this is just basic data cleaning process. After that, what was done is I used, in this example, let's say we need to predict if a person survived or didn't survive based on the variables we have. So we need to use for that some machine learning model. In this case, I used XGBoost classifier. XGBoost is a gradient boosting based model. So it was trained, and we see that it was the prediction was 0.8 when the prediction accuracy. So let's say we train the model, as I was saying. After that, after model training, we just need to feed like the trained model here, the pred model, which was the trained model, to sharp explainer, and then sharp values are generated based on this explainer and X, which was our initial data set. So when we generate these sharp values, we can use this matrix for different visualizations. For example, here it is the global feature importance based on sharp values. We can see, for example, so if the feature has high value, which means in this case female was encoded 1 and male was encoded 0. If the feature has high value, which means the person has higher probability to survive, because the person is on the right side of this graph, and if the feature had lower value, which means male, they are on the other side, which they had lower probability to survive. But for example, in here, the title code, it was Mr., Mrs., or other higher titles. So if the person had higher title, for example, doctor or some other kind of titles, it was important in the model's decision that he was survived. It's also important to see that family size, bigger family size, also contributed the person not being survived because the person had to take care of the family and gather them together, and people who were alone had higher probability to survive. Anyway, it gives sharp values. Not only we can do the regression analysis and clustering on the sharp values, but also it gives us very interesting view of the features, because when we trained with XGBoost, the feature importances were just like this. We don't have this kind of detailed feature importances about each person, each kind of feature and like detailed explanation. Also, we have this. This is how it looks when we want for just one instance to see, for example, why Rose from famous Titanic movie survived. And we can see that, for example, here, the blue features are the ones who are making her probability to survive lower, and the red features in red, they are making the probability pushing to up. So we can see that each feature here has some local importance. For example, her family size was 4, so it was decreasing her probability. But for example, she was female and it was increasing the probability to survive to 0.78. Anyway, the total probability of her survival was 82, and Sharp explains how each feature contributed to that. Yeah, that's it. Thank you. You can ask your questions now.
Any questions? Okay, this was a great presentation. So my question is, so SHAPE transforms the original X values to Z values. So by using some linear transformation like binary, can you explain that part and maybe bring a practical example? For example, like you're predicting the price of the house and you have like 2 features, like the number of the bedrooms, like 2, and like the square area, like how this transformation of the original data to binary format happens.
It's not a binary format. It's like values from -1 to 1, but it can be 0.7, it can be -0.2. It's not a binary format. It's just the same size matrix as initial matrix, but it gives us a feature importances for each instance in a local level, like not a global feature importance, but local. But I will explain how it works. So let's imagine we have not 2 features. Let's imagine we have 3 features. A data set with 3 features. House price, depending on, let's say, the location. What else? Number of rooms, location, number of rooms, and maybe something else. Let's say pets allowed or not allowed in this house. So based on this, the house price is decided. And then we give these values to Sharp, and what Sharp does, it takes we have 3 features, A, B, C, and then Sharp, the algorithm works as follows. It takes 2 features together, and then it runs linear regression locally with these 2 features. And then it samples again another 2 features, and then it runs linear regression locally. And then it samples all 3 features depending on from which order each feature joined, like 2 features, and then adds 1 more feature and runs the regression locally. And each time it tracks how this local linear model changed after adding 1 more feature, and based on this, it calculates the feature's marginal contribution to this coalition, which decides the house price. So then calculating this marginal contribution locally, it gives us each features, like let's say feature that pets are not allowed or allowed in this house, it was contributing 0.1 based on these local linear regressions that it runs, and then calculates the marginal contribution each feature added when the feature joined to the order. That's how it transforms the initial data to these coefficients, which is local feature importances. I don't know if I could answer. I would use actually whiteboard, but I don't know if I'm allowed. Oh, yeah. But did I answer your question, or should I continue on the whiteboard?
I think that's good. Yeah, my question was more like, let's say if you're running a regression model, that no longer will be like an instance explanation, right?
Uh-huh.
So how is the instance explanation like done? So let's say like if you have just one row of the like that you are trying to explain. So if you're running a regression model, so you can't run a regression model based on just a single row.
I see.
So because you need to have several data sets to be able to construct a linear regression model, right? So that's I was trying to understand. But maybe we can talk later.
Okay.
Thanks.
Any other questions?
Yeah, so first of all, really good presentation. I especially like that you showed how you could use explainers as conventional data analysis, not just about us interpreting the explanation. So I'm just curious if you have other examples of where you can use explainers within a data analysis pipeline.
Yes, I actually, it was my dissertation, so I did a lot of examples on different data sets. But there is another technique which is similar to SHAP, it's called LIME. So LIME is also, it can be used in similar way as SHAP, but I used LIME and SHAP both in the same context as a conventional data analysis tool, and I find out that LIME is not giving us the clusters as good as SHAP coefficients, because LIME is not using feature coalitions, but it is using for example, it is taking the proximity of other instances to instance of interest, and that's how it calculates Wait, I think I got lost. The question was, are there other examples? Yes, I did on different data set except loan. I did also this example on patient readmission, the diabetic patient readmission data set. It was to predict if the person will go to the hospital within next 30 days or will not go to the hospital. It was done also on, so this was classification, but this example works also in regression, linear regression example. And then you do the SHAP clusters. It's so bad I don't have a picture here. It was very demonstrative. Then you do the SHAP clustering and you map it back to this original data set. You can see the clusters that, for example, let's say our data, no luck. Okay, thank you. Oh, it won't be? Oh, I have here, nice, okay. So, so it was, for example, in linear regression, it was like this data, and this example I really liked. And when I was using linear regression on this data, it was just fitting one line, which usually would do. But when I did this SHAP example, SHAP clustering, and I saw that there are, for example, some data points that based on SHAP clustering, they are not fitting like this line, but we are fitted like this. And so many examples you can play to with different data set. It works on regression, it works on classification, just feeding the data and the trained model, and it gives you coefficients which you can play with a lot. It's interesting.
If there are no questions, I think we can have a break, and we will continue with the sessions at 3:30. Thank you.
Thank you. Thanks.